Welcome to This Explainer. Today we're going to take the invisible, microscopic chaos of atoms and turn it into what it really is, the ultimate reality show drama. We are talking about intense bonds forming, violent breakups, and honestly, savage partner swapping. By the end of this, you won't just see chemistry as a bunch of boring equations on a whiteboard, you're going to see these dramatic storylines playing out in the real world all around you.
Just think about this for a second. What are you digesting lunch? A rusting iron gate outside your house, and, say, that half-empty bag of potato chips sitting on your kitchen counter, what do they all have in common? They aren't just random objects. They are active battlegrounds for invisible non-stop chemical battles happening right in front of our eyes. Atoms are constantly rearranging themselves, and today we're going to give you the exact playbook to understand how they do it.
So here's our roadmap for this rapid revision. 1. Spotting a reaction. 2. Balancing the chaos. 3. The reaction playbook. 4. The redox game. And finally 5. Everyday chemical villains. Let's get right into it.
Starting off with Section 1, Spotting a Chemical Reaction.
So, how do we actually know a reaction is taking place? I mean, we can't exactly ask the atoms, right? Instead, we've got to use the detective's checklist. If you mix substances and suddenly see a gas evolving, like imagine dropping zinc into sulfuric acid and watching hydrogen gas bubble up, that is a massive clue. A sudden color change? Yep, chemical reaction. A drastic temperature change, like when you mix quicklime with water and it gets literally boiling hot, another huge clue. We also look for changes in physical state, and finally the formation of something called a precipitate.
Now, I want to pause on that last one for a second, because it's actually kind of tricky. A precipitate is this insoluble solid that just suddenly appears out of nowhere when two perfectly clear liquid solutions get mixed together. It's not like dropping a handful of sand into water where the solid was already there to begin with. No, this is a brand new solid magically born from a liquid reaction. For example, if you mix potassium iodide and lead nitrate, you get this striking, bright yellow solid that settles right at the bottom. That is a chemical reaction literally screaming at you.
All right, moving on to Section 2, Balancing the Chemical Chaos.
Okay, so now that we've actually found a reaction, we've got to write it down as an equation, but it has to obey an absolute rule of law, summarized perfectly by Antoine Lavoisier. Mass is neither created nor destroyed in a chemical reaction. This is the law of conservation of mass. It basically means you can't just magically spawn new atoms, and atoms definitely can't just vanish into thin air. The total mass of the reactants crashing the party on the left side of your equation must perfectly equal the total mass of the products leaving the party on the right side. And that, my friends, is exactly why we balance equations.
But what happens when those equations get, terrifyingly complex? You're going to need a secret weapon. The traditional hit and trial method, yeah, it's fine for the simple stuff, but for massive equations, it just eats up your time. Instead, you got to use the ABCD math trick. You just assign variables A, B, C, and D to your molecules, write super simple algebraic equations for each element, assume A equals 1, and just solve for the rest. If you end up with a fraction, no big deal, just multiply the whole thing by the denominator to clear it out. It is foolproof and lightning fast once you get the hang of it.
And hey, while we're balancing everything out, we absolutely cannot forget to account for energy. Reactions essentially have two contrasting energy personalities. On one side, we have endothermic reactions. These selfishly absorb heat from their surroundings just to make the reaction happen. Think of photosynthesis in plants absorbing sunlight. On the flip side, we have exothermic reactions, which generously release heat. Digestion is exothermic, and like we mentioned earlier, mixing water with quicklime releases so much heat. It's pretty much the classic exothermic example.
Which brings us to Section 3, the reaction playbook. Let's dive into the core types of reactions. And honestly, the best way to think about this is like high-stakes relationship drama. First up, we've got the combination reaction. A plus B equals AB. This is a beautiful thing. Two or more single reactants finally get together to form one single happy product. A really great example of this is calcium oxide and water teaming up to make slaked lime. It's just two separate entities completely merging into one brand new identity. But as we all know, not all relationships are built to last. Enter the decomposition reaction. AB breaks down into A plus B. This is the dramatic breakup. And just like real breakups, it actually requires a push of energy to split them apart. You have to supply heat, electricity, or light. For instance, if you take white silver chloride and leave it out in the sun, the light energy literally breaks it apart, leaving you with raw gray silver.
Now, before we get into the really messy drama, we've got to talk about the catalyst. Think of a catalyst as the instigator friend. You know the one. They speed up or slow down the chemical fight, whispering in everyone's ear, but they never actually throw a punch themselves. They stay completely out of the actual final product. They just change the speed of the whole reaction.
So, to understand who actually wins in these chemical fights, we use the reactivity series. Think of this as the ultimate power ranking for metals. Up at the top, you have the absolute heavyweight champions like potassium and sodium, insanely reactive. As you go down the list, they get weaker and weaker. A fun little trick students use to memorize this order is the mnemonic Katrina Nekarmangi, which translates to Katrina asked for a car. The starting letters map straight to potassium, sodium, calcium, magnesium, and so on. You definitely want to remember this ranking because the top tier entirely dictates the drama. And this brilliantly illustrates exactly why that power ranking matters. Case in point, single displacement. This is where a stronger, way more reactive element literally kicks a weaker one right out of its relationship. If you take a top-tier metal like zinc and drop it into a solution of copper sulfate, zinc completely flexes its muscles, kicks copper entirely out of the compound, and forms zinc sulfate. Poor copper is just left all alone as a solid sitting at the bottom. But hey, sometimes the drama is completely mutual, and that brings us to double displacement. This is the ultimate partner swap. AB plus CD becomes AD plus CB. Just imagine rival sports fans at a game who decide to mutually swap friends so everyone is happy with their new ions. Both compounds exchange their positive and negative parts to form two entirely new compounds. The whole shebang.
A classic, total exam favorite example of this is mixing clear barium chloride with clear sodium sulfate. They do this massive partner swap. The sodium grabs the chloride to make simple salt water, but the barium grabs the sulfate. And barium sulfate is an insoluble white solid. It suddenly clouds up the water and settles to the bottom as this stark white precipitate. It's incredibly visual, and it's practically the perfect example of double displacement.
All right, shifting gears to Section 4, the redox game. In this corner of chemistry, elements play a constant super high-stakes game of molecular tug-of-war between two competing concepts. Oxidation is all about gaining oxygen, or alternatively, losing hydrogen. On the complete opposite side is reduction. Reduction is when an element loses oxygen or gains hydrogen. They are total, complete mirror images of each other.
But here's the absolute secret to all this. They literally never happen alone. Redox is simply oxidation and reduction happening at the exact same time. It's a trade. If one element is getting oxidized by gaining an oxygen, well, it had to steal it from somewhere, right? That means another element is simultaneously acting as the reducing agent and getting reduced. They are permanently locked in this chemical dance.
And finally, Section 5, Everyday Chemical Villains.
Let's bring all this chemistry right back to the real world. First up, we've got the Corrosion gang. This is a notorious gang made of oxygen and moisture that slowly, quietly eats away at shiny metals. When they attack iron, it forms hydrated iron oxide, which we all know as rust, that flaky orange layer that just constantly falls off, exposing more iron until the whole thing is destroyed. When they attack silver, it turns black from hydrogen sulfide in the air. When they attack copper, it turns a chalky green. To stop them, we have to build defense armies. We coat our metals in paint, oil, or apply a really strong layer of zinc, which is a process known as galvanization.
Our second major villain? Rancidity. This is when oxygen relentlessly attacks the fats and oils in our favorite foods, completely ruining their taste and giving them a foul smell. Have you ever wondered why your potato chip packet is mostly air? Well, it's actually not air at all. Food companies literally pump the bags full of nitrogen gas specifically to push out the oxygen and fight off rancidity. We also use refrigerators, airtight containers, and antioxidants as our primary defenses against this kind of chemical spoilage. So we've gone all the way from the microscopic math of balancing equations to the rust on your front gate and the literal gas inside your chip bag. I want to leave you with this final thought. Look around you right now. Which invisible chemical battle, whether it's an oxidation attack, a slow decomposition, or some silent combination, is slowly altering your physical world without you even noticing? Keep your eyes open and stay curious.